Can you guys see my screen?
Yes, sir.
All right. Ish, guys, with electricity, let's just go straight into doing the questions, né? But let me just, what have I done? Let me just provide you with a little bit of some theory, yeah? Let me provide you with a little bit of some theory from the top of my head, the things that I think you need to know. Because this is quite a long topic, yeah? But yeah, let's start. Ne? So first things first, guys, you need to remember the whole of electricity from grade 11, right? Series circuits and parallel circuits, right? So what do you guys know about a series circuit? Tell me two important things that you need to know about a series circuit.
The current is the same and their voltage dividers.
Yes, right? So two important things. Current is the same, then voltage divides, right? Voltage divides. That's very true, right? And since when we say voltage divides, it goes to where, okay, let's rather say most goes to where there is high resistance, right? So let's just draw a simple series circuit. So this would be your cell or your battery. The wires connected like that. Then if you have a resistor here, another resistor there, and as you can see, between resistor 1 and resistor 2, there is no branching here, right? So there's only one path for current to flow, right? So to get from one side of the terminal to the other terminal, there's only one path for current to flow, right? So, and also from resistor R1 to resistor R2, there is only one path for current to flow. So we say that these are resistors in series, and for resistors that are in series, they have the same current. Yeah. So think of current as cars that have to travel through this wire, right? So if 5 cars need to travel through this wire, if 5 will pass here, 5 will also pass here, right? So the number of cars that would pass here is the same as the number of cars that would pass there, right? But then what is resistance, right? So resistance is the opposition of flow of a charge, right? So the cars would represent the charges, right? So basically, like the charges, the electrons are the ones that are flowing like that, right? So resistance is opposition of charge. So if there is high resistance here, let's say this one is maybe 5 ohms and this one is 8 ohms, right? The voltmeter here or the EMF, let's say it was 10V, right? So most of the 10V would want to come to this 8 ohm resistor, right? Why is that the case? Remember that voltage is more of like the force to push the charges, right? So the force of pushing those charges through this wire, right? And resistance is the resistance of flow of those charges. So here it's quite easier, right, for the charges to pass here compared to here, because here there is more opposition, right? So where would we need more force to push the charges through? We would need more force here at the 8 ohm resistor. That is why the voltage, most of it comes to the 8 ohm resistor, if they ever ask you why, right? Are we all on the same page with that one? So you need to know how to calculate the total resistance in series. So how do we calculate the total resistance in series? So the total resistance in series, you just add the resistors. So it's going to be R1 plus R2. If there are many resistors, then you'd add more, right? Yes, right. So And remember Ohm's law, right? So Ohm's law says that R equals to V over I, right? So if I want to calculate the R or the V or the I at any point, let's say I want to calculate it here on R1, I need to use the resistance R1, I need to use the voltage of R1, and I also need to use the current of R1. So basically here, R1 would equals to V1 over I1, the current that passes here, right? Same thing would, if I want to use the Ohm's law here, it would be R2 equals to V2 over I2, right? If I want to calculate the total resistance using Ohm's law, I can say that R total is equals to the total voltage over the total current. So we use this formula for a specific scenario. You don't just put in any resistance and put in just a random voltmeter reading and a random current. It should be for that part specifically that you are calculating. You'll see when we do more of the problems what I mean. So this is more or less what you need to know about resistors in series. Then let's talk a little bit about resistors in parallel. Right? So resistors in parallel, now they're opposite. So resistors in parallel are current dividers. Instead of being voltage dividers, they are current dividers, and voltage is the same across parallel branches, right? Can you see I'm using the word branches, right? So the branches that are in parallel with one another, they have the same total voltage. I'll show you why I'm using this word parallel branches, not just parallel resistor. You'll see. Let's connect a simple parallel circuit. Name a simple parallel circuit. Right, so let's call this R1 and call this R2, right? This is the voltmeter reading the EMF, right? So these cases that we're dealing with now, there's no internal resistance that we're talking about here for now. So for resistors in parallel, we said that the current is divided, right? So whenever you do an electricity equation, just draw how current would flow in that circuit. Yeah? So, okay, gonna give the relay. We would have a small one, then a tall one, right? Just draw how current would flow in the circuit. So current would start from the positive end, right? Flow in that direction. So the total current is the current that comes out of the battery, right? So it comes out of the battery, it travels, then it passes here, still the total current, right? But then when it gets here, some of the charges would flow in that direction and some of them would flow in that direction. The ones that flow on the upper branch, we can call them current 1, and the ones that go to the lower branch, we can call them current 2. Can you see what happened there? That's what we mean when we say the current is divided across the parallel branches, right? So the current that goes to the upper branch and the current that goes to the lower branch, when we add them, they need to give us the total current because they both come from the total current. So I can say that I total is equals to I1 plus I2, right? So then they would travel like that, like that. Then when they get here again, another point where they need to meet again, they would then give us the total current again. So this would be I1, this would be I2. They would give us the I total again. They would give us the I total again, and the I total would go back to the battery, right? So always draw your arrows, right? Just right before you answer the question for any electric circuit. Yeah? So what can happen is that they can just do things to confuse you. Um, maybe add another resistor here. Okay, before we do that, let's say the voltage here, if it's V, the voltage for this whole branch the voltage for this whole branch, the whole branch would also be V, and the voltage for this whole branch also would also be V, right? It wouldn't change. The voltage here and here and here would be the same, right? So that's what we mean by saying that the voltage is the same across the branches, right? So let's see what would happen if we add another resistor here. I add another resistor here, R3, right? So by adding another resistor R3, you notice that R3 and R1 are in series with one another. There's no branching of the wire between these two resistors. It's just a straight wire that is connecting them, right? So they are in series. So they would, remember we said that the current that goes here on the upper branch, you can call it I1, right? So the current that R3 and R1 would receive would be the same current. Yeah? But then now the voltage would divide because of R1 and R3 are in series, right? So the voltage across R3, if they put a voltmeter here, it wouldn't be the voltmeter reading of this one. It wouldn't be the same as that one. But then if they put a voltmeter like this to measure the voltage across the entire branch, it would still give us this value, right? So I can say that, okay, the voltmeter reading of resistor 1 plus the voltmeter reading of resistor 3 is equals to the voltmeter reading of resistor 2, and it is equals to V, the original. Do you guys agree? Right, I just want you to see these simple things. They can combine different circuits, right, into one. I need you guys to be able to notice that, right? So how would we calculate the resistance in parallel? So to calculate the resistance in parallel, basically R parallel is equals to 1 over the resistance of the first branch. I'm not saying it's the resistance of resistor R1, but then the first branch plus the 1 over resistance of another branch. If there are many branches, then do it like that. Ne? So basically in this scenario, our R parallel would be 1 over, okay, remember this is 1 over R parallel, right? So our R1 would be the resistance of this entire branch. Our R2 would be the resistance of that branch. If there are 4 resistors here, for R1, you would add all of them. Same thing goes with this one at this lower branch. If there are 5, just add all of them, then it would be your R2. Do you guys have any questions? All right, let's move then. You would then have what we call this. This one is very interesting. It's called a combination circuit. Ne? It's called a combination circuit. Combination circuit. Ne? So this is just grade 11 revision. We're not yet into the grade 12 stuff. Right? A combination circuit combines a series and a parallel circuit in one. Right? So this is how it would look like. And you don't have to cram all the circuits. You can tell by the how the current flows in the circuit, whether it's a combination or if it's a parallel or a series circuit, right? No need to cram the circuits. So let's say here they put a resistor here, call it R1. Then there would be some branching here. Then we have R2. Then another one here, R3. Then these two combine again at this point, then go back like that. Yep. So this is a combination circuit. Why do we say that this is a combination circuit? This circuit, this resistor here, it's in series with the battery, but these two, they're in parallel with the battery. Oh, so that makes it a combination circuit. So how would current flow in this circuit? It starts from the positive terminal, right? Starts from this positive terminal. It's the total current that comes out of the battery. And you see that here, the total current would pass through R1. So the current here, it's still I total that passes through here. Then the total current would pass and get here at this point where it divides, the point of division, right? So some of it would go there, I can call it I2. Some of it would go down there, I can call it I3, right? So then this resistor would receive I2, this resistor would receive I3, then they would meet again here. I2 and I3 would meet here again to give us the total current again, right? So they would put a an ammeter here, right? Put an ammeter here. Then they would ask you to calculate the current on this ammeter, but you don't know how would you do it, right? You don't know how you'd have to do that one, right? But then look, you can use this resistor because of the current on this resistor is the total current, and also the current on this ammeter is also the total current. So if you get the current passing through this resistor, it's the ammeter reading. Do you guys see it? So what else happens here in this combination circuit? So this series circuit is in series with this one. This series resistor is in series with this one combined. So if I get the total resistance of this one, it's in series with this one. So therefore, current divides, right? So some current, if they give you a voltmeter reading here, V, the voltmeter reading across R2, V of R2 is not equals to V. It's because of this series circuit here, this series resistor. Some of the voltage needs to go here, then the rest would go there, right? The rest would go there. So this is also internal, how internal resistance also works. We will talk more about it when we get there, right? So you'd see that from that voltmeter here, from this EMF or this voltmeter reading, some of it would go here to that R1, and we call it V series. V series, and some of it would go to this branches, and we call it V parallel. And the V parallel would be the same across the branches. The V parallel would be the same here and also would be the same here, right? So from just simple definition of saying resistors in series divide voltage and resistors in parallel divide current, we can solve more complex problems from just that foundation. It's very important, guys. And that foundation also helps us explain how internal resistance work. Yeah? Do you guys have any questions on this one? So we can say that V parallel plus V series would be the V total. Yeah. So yeah. Another thing is that when this total current divides, current likes to go where there is less resistance. So if the resistance R3 is larger than R2, then more of the current would come to this branch because it wants to go where there is less current. So where there is less resistance. Yeah, remember that. So you'd have graphs. You'd have graphs on. You see this one. There is no internal resistance yet, right? Graphs where there is no internal resistance, right? So for graphs where there is no internal resistance, you'd see that the Ohm's law says the Ohm's law says that R equals to V over I, right? So if I want to show a graph showing the relationship between V and I, for example, I would say that V is equals to R multiplied by I, right? Then if I keep this constant, then you'd see that I would have a graph in the form y equals to constant multiplied by t, which is x, right? So y equals to ax, I would have a directly proportional relationship, right? So if I were to plot v here and I would plot current here, I would have a graph that looks like this, right? So this is v versus I. Then what would the gradient of this graph represent? The gradient would represent resistance. But in the exam, they can switch the variables around, take V and put it here, then take R and I and put it here, right? What would the gradient then represent now if the thing is like this? It would still be a graph that looks like this, right? But then what would the gradient represent? So now our graph would be I equals to V, okay, I equals to V over R, right? So I is equals to V, or rather 1 over R multiplied by V. So you see that now this would be our Y, this would be our constant A, this would be our X. So this would then be the gradient, right? So the gradient of this graph would then be 1 over R if they plot a graph like this, right? So just showing you what they can do in the exam just to confuse you. So they can do something like this. Then the relationship between, can you see these are for scenarios where there's no internal resistance. So the relationship between, let's see, the relationship between V and R, right? So, and we keep, is it between V and R or I and R? The relationship between R and I, ne? And we keep this constant. So R equals to V over I. So if this is a constant, this is Y, this is constant, this is X. So we would have Y equals to A over X. This would be a hyperbola that looks like this, where we have R here and we have I there, right? So you see the graphs, guys, you don't have to like memorize them. You can just understand how the equations came about. Yeah. Um, so let's now speak about internal resistance, what internal resistance is. So internal resistance, it's the resistance that the battery has, right, due to the metals that are within the battery, right? So before the charges go out of the battery, they actually lose some of their energy, right? So they, before, yeah, the charges go out of the battery, some energy would be lost, right? So how do we then explain how that works, right? So let's say here we have a battery, right? And it has this internal resistance. We usually show internal resistance as a small resistor within, then we cage the battery like that, within a cage like this, just to show that the resistance within this cage is the internal resistance, right? So this is how we would show it. Then now this resistor here, it represents the internal circuit. Then we would have an external circuit. So an external circuit, I can write it as R external. Yeah? So please note that R external can be a combination of different resistors that are connected in different ways. For example, it can be, it's not just one resistor, but it's different resistors. Let's say we have here these two resistors connected like this, right? So any other resistor that is not the internal resistance, it's the external resistance. So this here as a whole would form the external resistance, right? So would be our R external, right? But still, even if it's just one big resistor, you can see that R external and the R internal, they are in series with one another, because from this R internal to the R external, um, there wouldn't be any separation or division by a wire, right? So R external is in series with R internal, right? So I can do the R external in different ways. I can connect a resistor here and another one here, then connect another branch like this, right? So any resistor that is not the internal resistance is the external resistance. So still these ones combine, they are my external circuit, my external resistors. They are in series with R, right? So all of them combined, they would make a resistor that is in series with R. Yeah? So I will just combine them into one. Um, I will just combine them into one and call them R external for the purpose of explaining how this R internal works, right? So the internal resistor, we would treat it as any other resistor. You actually don't need the formulas that they came with to solve a problem with internal resistance, but they were made just to make things easy, right? But then we would treat it as any other resistor in a circuit, right? So remember, resistors in series are voltage dividers, right? So you would have the battery providing a voltage called V total, or the EMF, right? So you'd have the EMF of the battery, right? Which is the total voltage, total right? So now this total voltage needs to be divided. Some of it needs to go to the internal circuit, and some of it needs to go to the external circuit. The one that goes to the internal circuit, we would call it what? V internal. And the one that goes to the external circuit, we call it V external. Why is this happening? Resistors in series are voltage dividers. It's not something new, right? Remember here, where we had these two resistors in series, and we had the EMF. We had the EMF. Some of the EMF, we said that it's gonna go there, and some would go there. This is what resistors in series do, right? Same thing. They do the same thing here. Some of the EMF goes to the external circuit. Some would go to the internal circuit. So the one that goes to the internal circuit, we call it V loss, right? Because we don't use it, right? Our appliances would use the voltage that goes to the external circuit. Because of this one, it's lost within the battery itself, right? It's used, the voltage is used within the battery itself. So it's a loss, right? Then now we can find an expression for V internal and V external relating it with EMF. So remember, EMF is like the total voltage. V total is equals to V internal plus V external, right? You would have to add them, right? So you would have V internal plus V external, right? We can further rearrange this, right? So look at this thing here. The current that goes out of the battery, it's the total current. The total current would pass through this R, right? So the current that passes through this small letter R is I total. The I total would pass through the entire circuit as I total. There's no way it divides. Even when it passes through the R external, it's still I total, right? It's still I total, and we'll go back to the battery as I total, right? So the current at the R external as a whole is the same as the current that goes to the internal resistance as a whole, right? So therefore, if I want to apply Ohm's law on this small resistor R, I would have that small resistor R is equals to the voltage that goes to that small resistor R, which is going to be V internal over the current that goes to the small letter R, would be the I total, right? Then rearranging this, I am making V internal the subject of the formula. I have that V internal is equals to small letter r multiplied by it, Then I can take this, substitute it here, substitute it there, right? So EMF would then be equals to R multiplied by IT. Apply the Ohm's law as well on the R external. I would have that R external is equals to V external over the total current passes through R external, right? Over I total. So therefore, V external is equals to R external multiplied by the total current. Go and substitute this there, right? Plus R external multiplied by the total current. Are you guys not familiar with this formula? If I were to rearrange it, I would have that EMF is equals to, take out a common factor of current, it would be equals to small letter r plus R external multiplied by the total current. Then they don't usually write R external as R external, they just use a capital letter R for representing the R external. And this is where the formula comes from. But in reality, guys, to tell you the truth, this formula, you don't actually even need it, because you would have to treat this resistor as any other resistor, then solve your problem like you would solve it. But to make things easy, and so that you can answer the question much quicker, you can use this formula. Yeah? So there is this other question where you need to see the relationship between the variables on this formula. Very important, the graphs of this one. You'd see that the graph of the relationship between V external and current is not a directly proportional graph like we would see it. Where is it? Okay, I wiped it. Like when there is no internal resistance, it's not a directly proportional relationship like that. This one you would see a decreasing straight line graph. Why is it the case? We can explain it why. So graphs, right? So they would tell you that Elena, sorry, they will tell you that Elena has set up a circuit like this. Okay. Yeah. Elena has set up a circuit like this. So here you would have R, a rheostat. Let's say this is a rheostat. Yeah? So I can change this resistance, right? And by changing this resistance, the total current would change, right? Remember that if I decrease the resistance, then the total current would increase, right? Because current and resistance are inversely proportional, right? So if I increase current, if I increase resistance, current would decrease, right? Then how would then the fact that current has changed, how would it affect the external voltage, right? The value of this voltmeter here. Remember, this voltmeter here is measuring the external voltage, V external, right? And when is, so the voltmeter here, right? The reading here, it's either measuring V external or it's measuring the EMF. Under which cases is it measuring the VMF? Is the EMF, and under which cases is it measuring the V external? I will explain that one, right? So think about it. The total current, let's say I I increase the resistance here, right? I keep on increasing the resistance, then the total current would do what? The total current would decrease, right? The total current would decrease. Okay, let me not say I increase the resistance. Let's start by decreasing the resistance. I decrease the resistance, then the total current would increase, right? Because remember, current and resistance are inversely proportional, right? So because the fact that current is the one that increases, the current increases by me decreasing the resistance, how would the value of this voltage here be affected? So mostly this voltmeter reading is measuring V external. It's only one case where it measures the EMF, but as I change the current, most of the time it's measuring the V external. And it's only one case where it measures the EMF. So I can say that, okay, here the reading here is actually V external, right? So let's go to that equation. Our equation says that EMF is equals to V external plus V internal, right? So now I want to see the relationship between current and the reading here, which is V external. So what would I have to do? I would have to make V external the subject of the formula. So V external would be equals to negative V internal plus EMF, right? Negative V internal plus EMF. But then remember, I want to see the relationship between the total current and V external. So I can write this here as V external equals to negative the current multiplied by internal resistance. Remember, V internal is equals to negative I multiplied by internal resistance, is equals to I multiplied by internal resistance, right? Plus EMF, right? So I can rearrange this and write it as V external is equals to negative R multiplied by I plus EMF. Then relate this to a straight line graph. I can see that, okay, this would be my Y, then this would be my M, this would be my X, this would be my C, right? So V is my Y, current is my X, right? Remember, current is what I've been changing and seeing how it affects the V external. So from this graph, you can see that, okay, the gradient is negative. So this would be a decreasing straight line graph. And the y-intercept of that graph would be the EMF. So it would be a graph that looks like this, actually. It would be a graph that looks like that, where here it's the V external reading, and here it's the current. Yeah? So it's the current in the circuit. So we can see that here, when the current is 0, the reading on the V external is the y-intercept, which is the EMF, right? So when no current is flowing, the voltmeter here registers the EMF. This is also shown by the graph as well, right? So when current is 0, the voltmeter reading is the EMF. That is why I told you that this voltmeter here, most of the time is measuring V external, but it's only one case where it measures the EMF. So when is it measuring the EMF? When no current is flowing. Yeah. So this would then help you answer a lot of questions. But then in the exam, they wouldn't give you this graph because they already know that we taught you in class and they want to see your ability to come up with your own equations, right? And we will do questions so that you see how they ask these questions. Yeah. Do you guys have any questions so far? All right. If you don't have questions, then we can pass. Is there anyone who's confused? All right. Okay. No one is confused. Then let's pass. Then we can start doing the questions. You can do this one, guys. I'll give you 14 minutes, 10 minutes. But 10 minutes is a lot, Joe. Guys, are you done? Hello.
No, sir, no, we're not done.
No.
We're not done.
Today we have 2 hours. Remember that after here you have to go attend maths. Some people need to go attend maths, so we have to keep it strictly at 2 hours. So yeah, that's correct. Ne? You'll think about it as we answer the questions. So first things first. Let me put this mic here. First things first, you need to draw the arrows showing how current would flow in the circuit. Ne? So let's show them. It will come out like that. Then as the total current, it's the total current that comes out of the battery. It would flow in that direction, total current, right? Then when it gets here, it divides, right? Some of it would go up there. And remember here, you look, they showed you that this is current of ammeter A1. So we can say that the one that goes up, we can call it I1, or you can say it IA or IB, but let's just call it I1. Then the one that goes down, you can call it I2, right? Then I2 would flow past this resistor, past this ammeter A2. So the ammeter A2 is measuring the current that passes through this resistor R, right? Then look what happens when it gets on top, right? Look at I1. I1 would then further divide, right? I1 further divides into IA, can call it IA, and call this one IB, right? So look at the IA, it will pass through the 8 ohm resistor, right? Then it will come here, same thing, IB passes through the 16 ohm resistor, IB, then they combine here again to give us what? To give us I1, right? Then I1 passes through the ammeter A1, and it also passes through the 20 ohm resistor as well, right? Then I1 and I2 combines again to give us the total current that comes out of that combination, and that total current would then pass and go back to the battery. The internal resistance would also receive the total current. So this was a nice question. So this here, everything here is our external circuit. It's in series with the internal circuit. So within terms of the voltage, right, some of the voltage would go here, some of the EMF would go there, we call it V internal, and some of the EMF would go to the external circuit, and we call it V external. Yep. So let's see how we would answer this question. If you've done this, guys, you are ready. With switch S closed like that, the current passing through the 8 ohm resistor is 0.5. Where is the 8 ohm resistor? This is the 8 ohm resistor. The current here, they say that it's 0.5 A. Current here is 0.5 A, right? State Ohm's law in words. Ohm's law. What does Ohm's law say, guys? I forgot it.
Let's say the EMF across the conductor is directly proportional to the current in the conductor at constant temperature.
The potential difference, the potential difference. Sorry, use the examination guideline, but it says the potential difference, not the EMF. Examination guideline. Thank you, Vianney. 4.2 says calculate the ammeter reading on A1, right? So how would you calculate the ammeter reading on A1? How many marks is this? 4 marks. So remember, I told you that the ammeter reading on A1 is the same as the ammeter reading or the current passing through the 20 ohm resistor. How would you guys do it?
There
Yes.
I calculate the voltage for 8 resistance and I got 4
Mm-hmm.
V.
Okay.
Then
You calculate here, you got 4V here.
yes,
Okay, then what are you gonna do with that 4V? Also on the 16 ohm here would also be 4V, right?
also yes. And then I
Mm-hmm.
calculate the current for 16 resistance. Then I
Mm-hmm.
got 0.25.
Yeah, that's a good approach. So let's write it down. 4.2. You calculated the voltage on the 8 ohm resistor. Resistance is equals to voltage over current, right? So resistance
Yes,
is 8 equals to the voltage. You're looking for the voltage across the 8 ohm resistor over the current through the 8 ohm resistor was given to us as 0.5. Then the voltage through the 8 ohm resistor would be 8 times 0.5, which is 4V, right? Then we got, that's the first step of answering the question. Then because we say that resistors in series, sorry, the resistors in parallel um, have the same potential difference. So therefore, the potential difference here and the potential difference there would be the same. So you say that this is this is 4V. Now we have the resistance, we have the voltage here. We can calculate the current, right? So we can say resistance is equals to voltage over I. Remember, the resistance now is 16 equals to the voltage across the 16 ohm resistor. You said that it's 4, right? As well. So 4 over the current across the 16 ohm resistor. So what did you find the current across the 16 ohm resistor to be?
I got 0.25.
You got
0.25.
0.25 A, right? So here the current here, it's 0.25 A. But then look at this thing here, how beautiful it is. 0.5 A and 0.25 A. You see this 0.25, it's IB. This 0.5, it's IA. And when we combine IB and IA, they combine to give us I1, right? So I1
Yes.
is equals to 0.5 plus 0.25, which is 0.75. Then therefore, the current here is 0.75A. Also here it's going to be 0.75A. They can ask you to calculate the voltmeter reading across the 20 ohm resistor. You have the current, you have the resistance, you can do that if they ever do ask
Sorry,
you.
sir.
Yes,
Sir,
yes.
is it fine if I use the ratio between the resistance? Is it fine if I use the ratio between the two resistance, which is 1:2, and then since I know the resistance across the the current across the 8 ohm resistor, and I will know by its half of the current across the 8 ohm resistor, is I
Hmm.
still get the same answer, which is
Yes,
0.75.
it also works that way. Yeah, it also works. Yes, it is. I think you know, Bushe. Um, so that's the beauty of it, guys. There are too many ways to doing this, right? There's no just one universal way. As long as you're gonna get the right answer. 4.3, they say that the device R delivers a power of 12 W. Calculate the reading on ammeter A2. So here the power here is 12 W. What would you do with this power? Because you need to do something with it, right? I know that power is equals to V squared over R. Hmm.
Sir,
Yes.
So I got the voltage across the 20 ohm resistor.
That's what I will also do. Is there any
And
other formula? Wait, sorry. Is there any other formula that relates power with current? Is
yes,
it power equals
P equals to VI.
VI, right? So if we get the voltage first, then we can calculate the current. Because for us to be able to calculate the current, we need V and we also need power. If we have the two, then we can calculate the remaining one, right? So we can go get V first. How did you get it?
So I got the V for the 20 ohm resistor, which
Mhm.
was 15 volts,
Then
and then
you added
yes,
it with
and then I added it.
that would also work. But another way that can you see, guys, you did it without using the formula, yeah, external, sorry, yeah, the EMF formula. You did it without doing that, but you can use it here. It can work to our advantage. Let's use it, right? EMF is equals to, do we have the total current? Do we?
No, no, sir, we don't.
But do we need it to be able to calculate this? Okay, they gave us the internal. Okay, it's gonna be a long one. It's gonna be a long one. Let's just leave it. Let's just go with your way. Because that one was gonna be a long try. So yeah, let's just just continue with that step. So we're gonna calculate the voltage reading across the 20 ohm resistor. Then we're gonna add it with this one. Then it will give us the voltage of this entire branch. And the voltage of this branch would be equal to the voltage of that branch, right? So let's do it. So on the 20 ohm resistor, we can say that R equals to V over I. R is 20, V is what we're looking for, voltage of the 20 ohm resistor over the current is 0.75. Therefore, the voltage across the 20 ohm resistor, how much did you get?
15 volts.
You got 15, right?
Yes.
15 V. So here we have 15 V. But what was the voltage of this other parallel branch was 4V. Therefore, the, the voltage of this entire branch would be 4 plus 15, right?
Yes.
So therefore, the voltage here that we would substitute would be 4 plus
19.
15, 19, right? So power is equals to 12 equals to 19 multiplied by the current. So therefore, the current would be 12 divided by 19,
0.63 amps. 63.
0.63A, right? Yeah, that's correct. That is correct. Any questions? Okay, here we have 0.63A. That's the current. I2, 0.63. Then can you see we have I1? Remember I1 here it's 0.75A. Then I2 here, as you can see, it's 0.63. Then the total current would be how much? What would be the total current, guys? The total current, remember, it's the sum of I1 and I2.
It's 1.38.
That's 1.38A. Now, calculate the reading on the voltmeter when switch S is open. So they want the EMF. Because remember, I told you that when no current is flowing, if you open switch S, you're cutting off this circuit, right? No current will flow in this circuit. So if no current is flowing, current is zero, then this voltmeter here is measuring the EMF. So the hidden question is actually asking you to calculate the EMF. So we can use the EMF formula. So EMF is equals to R plus R external. Do we need to go this route? Multiply by I. I don't think it's necessary for us to go this route.
So
We can,
we don't have R.
yeah, we don't have R, but then we have the external voltage, right? The external voltage is 19. Do you guys agree? Because of the voltage of this entire branch is 19, the voltage of that entire branch is 19. So V external is 19, right? But we also have V internal. So we can write this formula to suit our situation. We can write it as EMF is equals to I R plus IR, right? So this here, it's, remember, it's V external, so it would be 19, right? So this, we would then have to substitute the values. So EMF is equals to then total current 1,38, right? Internal resistance is 1 plus total current, oh, sorry, this whole expression is our V external, right? So our V external is 19. So this is why this question was 3 marks, because it was straightforward. So it would be 20,38 V. Do you get it, Ubush? Ubush, do you understand this one? Because even though we don't have the value of R,
Yes,
we
I
don't
do understand.
we don't need it to solve this problem. You can always rearrange this formula to suit the case that you're dealing with, right? So yeah, we're done with that one. It is an interesting question, and it shows you how you must be able to understand the basics before you can answer any other question. The basics are what is important here. Here's the next one. Sorry, what time is our session ending? Is it 7:30? Right. Can you guys please accept the person who's in the lobby? Guys, can you hear me? Please confirm if you can hear me. All right, are you done with this one? Molweni. Okay, Ubuhle would do question 1.5.3. 5.1.3. Ubuhle would do this one. Then Jaden would do this one. Then I don't know who else is in the meeting. Who wants to do the first one? Marava, can you do this one? Then who wants to do 5.2? Destiny, can you do this one?
No, sir. I'm
Yeah?
so sorry. No,
Okay.
sir.
We will do it together. You and I will do it together. This one is ours. Yeah?
Okay.
We will help each other.
Okay.
So I'll start by reading the statement. They say that a battery of unknown EMF, they don't know the EMF and internal resistance. So they don't know the EMF and the internal resistance. Oh, so they know the internal resistance. The internal resistance is 0.5. This is the small letter R. 0.5 is connected to 3 resistors, right? A high resistance voltmeter and an ammeter of negligible resistance as shown. The reading on the ammeter is 0.2. So here is 0.2A, right? As you can see that this would be our internal circuit, then the remaining 3 would be our external circuit. How would current flow here? Crazy. But let's show with the arrows. Current would go out of this positive terminal as the total current, and 0.2. It would pass here as the total current. Then as you can see, when it gets here, it needs to divide, right? Some of it would go up there, you can call it I1. Some of it would go down there, you can call it I2, right? So I2 would pass through this branch here, right? So meaning that the 4 ohm resistor would receive I2, the 8 ohm resistor would receive I2, and they gave us the value of I2 as 0.2A. So we know that here would be 0.2A, also here would be 0.2A. Can you see, because we have the 2 variables on this resistor and 2 variables on that resistor, we can calculate the missing one, which is the voltage. You can calculate the voltage across this one. You can also calculate the voltage across this one. And when we add the voltages, it would give us the voltage of the entire branch. Then the voltage of this branch would be equals to the voltage of that one because they are in parallel. Can you guys see it? Interesting, ne? Then here you see that you would have I1 passing through there. Then remember, voltage, a voltmeter, current does not go to a voltmeter because it has very, very high resistance such that no current would want to go there. So it would go this. I don't make a mistake of saying some of the current would go there. Current would just go like that. Then, pass through this point as I1 again. Then remember I2, right? So when I2 and I1 meet again, here at this point, they give us the total current, which would pass through the internal resistor, right? So you can see that this voltage here is measuring the voltage of the external circuit as a whole, right? That is going to the parallel circuit. It's measuring the voltage of this entire branch, which is equal to the voltage of this branch. So we can calculate the voltmeter reading if we want to. We can calculate the voltage here and the voltage there, then add them. It will give us the voltmeter reading. We already answered the question, guys. 5.1.1. Calculate the reading on the voltmeter. Can you see, guys? They want us to calculate the reading on the voltmeter. So the easier way to do it, can say that R equals to V over I. Combine these two resistors to make one resistor, right? It's going to be a 12 ohms, right? So go like 12 ohms is equals to voltage reading over the current that's going to be passing through this branch is 0.2, right? 0.2. Then V would be 12 times 0.2. How much do you get? 2.4. I get 2.4 V. Alternatively, if you like to do things the long way, calculate the voltage here, calculate the voltage there, then add them. It should give you 2.4 as well. 5.1.2. Sorry, Kgothatso, yo. Ish, it's a ditaba tsa. So sera re tla replace Kgothatso mo ra mmea.
I'm confused. Why are you confused? Number one, where are you?
Why re dira so? To calculate the voltmeter reading there.
Where
12.
Yes. Okay. Why do we get 12 as resistor?
Okay, 12 is a combination of these two, right? If you combine these two into one resistor, you'd have a 12 ohm resistor, right? But still the current that is passing through this 12 ohm resistor would still be 0.2A. Then you have 12 ohms here. It's a combination of these two, right? 4 plus 8 is 12. The current through this branch won't change. It's still 0.2, even after I've combined the two resistors, right? So if the current is 0.2, the resistance is 12, I can find the voltage across the entire thing now. It won't be the voltage across this one and the voltage across this one. It will be the voltage across the entire thing. Do you get it, Kgothatso?
Yes, sir.
You sure? Okay. That's why I said that alternatively, this is a 3-mark question. There was no need for you to do a long dry of calculating this one, then calculating that one, then add them. You can just do it in one formula. Yeah? 5.1.2, Jaden, calculate the total current.
So since we have the voltage, we'll find the current for the 2 ohm resistor, and then we'll add it to the current of this, to the 0.2.
All right.
Yeah.
That would work. That would work, right? So here we know that V is 2,4 V. So we can calculate I1, right? So R equals to V over I. So R of this 2 ohm resistor is 2 ohm. V is 2,4 over the current I1. So therefore, or the current across the 2 ohm resistor. So therefore, current across the 2 ohm resistor is 2,4 divided by 2. How much do you get? Jaden?
So sir, I got 1.2.
That's 1.2 A, right? So it makes sense that most current went here, right? The current here is 1,2. The current on this branch is less because this branch has a higher resistance of 12, and this one is just 2. So once we get this current, remember I1 plus I2 gives us I total. We can say that I total is equals to I1 plus I2, which is going to be 1,2 plus 0,2, which is going to be 1,4. A. Are we all on the same page, guys?
Sir,
Yes.
ke kgopela ho botsisha that voltage ke the total voltage.
The external voltage is not the total voltage. Remember, the total voltage is EMF. That's the external voltage.
Oh,
There's also some internal voltage. So remember, current is flowing. So the voltage here would be reading the external voltage, not the EMF. If we switch this thing off, the value here would increase. If we switch this circuit off, the value here would increase, showing that it's now measuring the EMF, which would be something bigger than 2,4. It's not the total.
okay,
This total.
so the reason why re shumisha 2,4 go calculator ntse ba re calculator. Oh, the reason why re shumisha 12 ya the resistance again re nyaka V, it's because it's in parallel, and we know that in parallel connection voltage is the same.
Yes, that's true. I get it. 12V is the resistance of the entire branch, and therefore the resistance of the entire branch, we can use it to calculate the voltage of the entire branch. So here is no clear the voltage of this branch. We therefore conclude that it's the same as the voltage of this branch.
Okay.
Yeah, you are right. Ubuhle, are you ready for 5.1.3?
Yes, sir.
What was your approach?
I first calculated, yes, sir. I first calculated the parallel resistance
For the
by
total.
first adding the 4 and the 8, and then yes, for the total, for the parallel, for that resistance at that specific branch. And then I got what it's 1/12 plus 1/2, and then I got the inverse of that, which will be our parallel resistance, and I got the parallel resistance of 1,71 ohm.
So you notice that this 1,71 is the R external because there's no other resistor, right? So this would be the R external, right?
Yes, sir. And then I went into my EMF formula, and then I plugged in
The values.
the total current, yes, the values, the total current that was calculated first, which was 1.4, and then I multiplied it with my VR external, which is 1.71, plus my internal resistance, which is 0.5, and I got an EMF of 3.09.
So this is like you substituted everything into this formula because we have the small letter r is 0.5 plus the capital letter R, we just calculated it is 1.71. Remember, capital letter R is R external, right? 1.71 multiplied by the total current. The total current is 1.4. So 0.5 plus 1.71 multiplied by 1.4. Is it giving you the same answer?
3. It's 3.09.
Okay, 3.09. Let me check on my calculator just to confirm. Yes, 3.09. 3.09A. No, not A, but B. Yes, Itumele. Itumele, I can't hear you. I can't hear you properly. I think you are wearing headphones again. Just take them
Okay,
off.
so I want to about the V external. Isn't 2.4 volts the V external?
The Vx, let's see. 1 over 12 plus 1 over 2 to the power negative 1. No, it's 1.71. Why would you say it's you said it's 2,
I said my V external because I get into on the parallel thingy, on the parallel circuit, the voltage is the same throughout on those resistors. So I took my Ohm's law equation, which is R over V over I, then I made voltage the formula, which one times R, and then that R is our R total.
Rudy, really?
Ankere say my V external it go about 2.4 because go parallel circuit the voltage is the same throughout. So I didn't calculate the V external because I thought it's 2.4.
Yes, the V external is 2.4.
So and then Kimona more you calculated it. Oh, is it Nobuhle or something? Calculate the V external because now I substituted my IRS 2.4.
Okay. You did this. What did you do? Let's see. You said EMF is equals to IR plus IR.
Yeah. Then
Then
kare for the IR yo kala kare it over is my oh wait
1.4
yeah 1.40
multiplied by 0.5 plus
plus
2,
and then that was calculated. I said 2.4. I don't know if my calculator got
that's
wrong.
correct. That's correct. It should give you the same answer as ours.
Which means I punched the wrong thing because I didn't get the same answer, but the substitution is correct.
So you're saying 3.1 and 3.09 are not the same.
No, I'm saying I didn't get 3.1, which means when I punch, I substituted the correct thing, but when I punch on the calculator, I punched the wrong numbers and then I got 3.6, but the substitution is correct.
Oh, okay. Yeah, but yeah, that's very correct. Yeah, it's also fine if you did it this way.
Okay.
Yeah. Okay, thank you, ne? Destiny and Hotaz. Can you explain how would the voltmeter reading, the V external, right, change if the 2 ohm resistor is removed? Let's go back to this question, right? So you see that here the main idea is to know the relationship between V external and current, because that's the two variables that have a relationship. But then you can't change the current without changing the resistance. You need to change the resistance first. That is why I told you that here they change the resistance first. They tell you that, for example, they decrease the resistance. Then whatever change they've made to the resistance, ask yourself, the first thing you need to ask yourself, how will this affect my current in the circuit? How would it affect the total current? That's the first thing that you need to answer. So let's go back to this one. They say that the 2 ohm resistor is removed. How will this, number one, affect the total resistance? Then number two, how will it affect the total current? That's the first things that we need to ask ourselves. So by removing this 2 ohm resistor, we are removing a resistor that is in parallel. Therefore, the total resistance would increase. Do you guys agree with me? Destiny, are we on the same page? We remove a resistor that is in parallel. This is a resistor in parallel. When you remove a resistor in, write this down, guys. Write it down. When you remove a resistor in parallel, the total resistance would increase. When you remove when you remove a resistor in series, the total resistance would decrease.
So,
Yes, Destiny.
can I try and answer it first?
Yes.
Okay. I don't know if it's right though. Removing the 2 ohm resistor will increase the total resistance, which will decrease the total current, ultimately decreasing the internal voltage and increasing the reading on the voltmeter.
Yes, that's correct. But then you would lose a mark for not mentioning things that are constant. So let's try and answer it how they want you to answer it in the exam. But yeah, you do have an idea. That is correct what you just said. Yeah? So we'd say that the total resistance increase. Then we say, according to Ohm's law, right, the total current would decrease, right? So when the total current decrease, what is the relationship between the total current and the external voltage? You saw that the relationship is this, right? Where we have the V external and here we have the current. As the current increase, the V external decreases. So now our current has decreased, right? Therefore, the V external will increase in this case, right? Then mention that the EMF remains, and the EMF and the internal resistance remain the same. Then you get your full marks, guys. You get your full marks. Thank you, Ned Destin. Ubuhle Aren.
Yes, sir.
Ubuhle with a U. Ubuhle with a U idira.
Se kopela repeat mo nola remove a resist in parallel what.
What? This guy will Pretoria.
Yeah,
This guy's from Pretoria. I can tell.
yeah.
So when you remove a resistor in parallel, the total resistance would increase. Did you get that part?
Yes.
When you remove a resistor in series, the total resistance would decrease.
Yeah, sharp. Thank you.
All right. The opposite would be true, right? if you add a resistor in parallel, the total resistance would decrease, right? Then when you when you add a resistor in series, the total resistance would increase. So the opposite would be true. Just know one, then the opposite would just be true. All right. Let's move on to a more graph question. Let's move to a graph question. The rest you do them on your own. Take a look at this one. Here, you see they gave you the EMF and the V external in a different way, not in words, but in the form of a graph. Right, let's read the statement here. So they say that in the circuit, resistor R, there's the resistor R with 5,6 is connected together with a switch, an ammeter, and high resistance voltmeter there. Voltmeter there, it's measuring the V external. The resistance of the connecting wire and the ammeter may be ignored. The graph below shows the potential difference across the terminals of the battery as a function of time, right? So at time T1, they closed the switch S. So all along it was open, then they closed it, then the value here decreased. It changed from a 13 to a 10,5. So all along before T1, the switch was open, then current was not flowing, then the voltmeter was registering what? The EMF. So this 13 here is EMF. Then when current starts flowing, it's then the V external. So they gave you the V external and the EMF. Then you can then perform the calculation like you do in any other scenario, right? Information is just presented to you, but in a different way. They usually present information in terms of words, but then now it's in terms of a graph. It doesn't change how you'd approach the question. Yeah? Look at this one. They say that the ammeter, can you see guys, this question of showing the relationship between current and external voltage. It's very important, guys. Don't go into the exam room not knowing how to explain this question. Guys, please, I beg you. Nah, don't go into the exam without knowing this one. If it won't come as a multiple choice question, it will definitely come in the short answer questions. Yeah. So here, how will the voltmeter reading V external change if you increase the current to 4A? The total current increases. So as the total current increase, we know that as the total current increase, V external decreases, right? Our answer would then be decrease. Why is it decreasing? Give a reason by referring to the V internal, V of the internal resistance. Remember, EMF is equals to V internal plus V external, right? So this would be I multiplied by small letter r plus I capital letter R, right? So if I increase the total current, then V internal, what happens to V internal? V internal increases, right? So V internal increase, but then EMF has to remain the same. So what would happen to this one? This one would have to go down to balance. Do you guys see the relationship here? If I had like 5 is equals to 2 plus 3, then I increase this one, but I want my answer to be 5 still. I increase maybe this one to a 4 now, but I want my answer to be 5 still. This one would have to decrease to like something like a 1, so plus 1. So if this one goes up, this one must go down. Do you guys see it? But then one would argue and say that why, when we increase the total current, because the current and the V external, they kind of have a directly proportional relationship, because also look, V external, sorry, no, I don't want to say that current and V external have a direct proportional relationship. One can say, why can't we say that when current increases, V external increases? Because you can clearly see that V external is equals to current multiplied by R. Why, when we increase this, why doesn't this also go up? Who can answer this question? Why should we explain it in terms of what happens to the internal resistance first, and not just go straight into using this formula and say that as I increase, the V external has to increase as well? This is because that now here there won't be a controlled variable, because remember we said that we can't change the current without changing the external resistance first. We need to tamper with the resistance, then it will tamper with the current. So for us to increase this current, we actually decreased the resistance first. So can you see that two things that are changing? So we don't have a clear relationship here. That is why we can't use this to explain that as current increase, V external increase, because this is not constant, by the way. But then here, look, V internal is equals to IR. Internal resistance is constant, right? So when I increase the current, the V internal will increase. Do you guys get it? I can't hear you. Okay, I see thumbs up. Itumelong are no. Okay, Itumelong, which part don't you understand? Look, because like, look, there's a formula that says V external is equals to IR. From this formula, you would expect that when I increase I, V external would also increase, right? But then why can't I conclude just from this and say that as I increase, V external would also increase? I can't, because there's no like direct relationship that I can deduce from this formula. Why is that the case? Because from this formula, there's no controlled variable. R is not constant, guys. Like I told you that if you want to tamper with the total current, you need to tamper with the external resistance first. So I changed this, and also this changed, then it affected this. So I can't come with a relationship and say that because of V external increased, I also increase, or because of I increased, V external also increased. I can't use this formula to explain. But with the V internal, I have a relationship between V internal and current. Because why? From this formula, there is a controlled variable, because R is constant. It never changes. It's a feature of a battery. If I'm still using the same battery, it doesn't change. So this is constant. Then as total current increases, V internal, I would expect it to increase, right? So now, if I take a look at this one here now, there is a controlled variable. EMF is the same. It doesn't change because it's a feature of a battery, right? So because of EMF is the same, if I increase V internal, I would expect V external to go down to balance. I showed you an example using numbers. If I have 5 is equals to 2 plus 3, and I keep this one constant, I don't change it. If I increase this one to something like a 4, and I still want my answer to still be 5, this one should decrease to a 1. It should decrease to 1. So that I have 4 plus 1 is still 5. So can you see that as the first number increases, the second one needs to go down. So this one remains as 5. So how you'd explain it is when you change the total current, it first explain. So this is a process, guys. Let me kind of give you a generic process. You change you change the resistance, right? You change R external, right? Then it affects the total current, right? Then how does it affect the total current? You're gonna say it. Then how does the total current then affect the internal voltage? Then how does this change in internal voltage affect the external voltage? Then you then mention that EMF and internal resistance remain the same. Guys, now I'm making you cram. This is the process of answering that explain question if there is an internal resistor. So the first things first, you can't change the current without changing the R external. So in some questions, they might skip the fact that R external was changed first. They just give you what happened to the current, and then you need to explain what happens down this process. Just like this one, they told us that the current increased, but they didn't tell us how did that current increase? What happened for this current to increase? For this current to increase, actually the resistance was decreased first. The total resistance was decreased first. Then from there, you can continue with this cascade of explaining how things happen. Ne? I hope it makes sense now. Ne? So we're gonna pass. So remember I told you that for any physics graph, take a look at it as a maths graph, right? Look here, they gave you the equation that you need to use. But then a cruel examiner might not give you this equation to assist you. Then you would need to find it by yourself. How would you do this? Right? So from the formula, EMF is equals to IR plus V external, right? So we're gonna make V external, okay? Sorry, let's see. Let's write it the way it is on the formula sheet. It's R plus R multiplied by I. So the question here wants the relationship between R, you see this is capital letter R, and 1 over current, right? This is the relationship that the graph is showing. So this is our Y value, this is our X value. So from the equation, let's make the capital letter R the subject of the formula, guys. Do you guys agree that that's what we have to do, right? For any graph, we need to do that so that we know the relationship, right? We're gonna look for a formula that relates external resistance and current. So it's the EMF formula, right? So you can see that here EMF would be equals to R plus capital letter R multiplied by I. So I can write this as IR plus capital letter IR. This is EMF still. So transpose this to that side. I would have EMF minus IR is equals to I capital letter R. Divide everything by I. Divide everything by I. Then this would cancel that. That would cancel that. Then therefore R is equals to negative, EMF over I minus R. But then on the x-axis, they plotted 1 over I. So that I see it clearly. I can see I here. So I can write this as 1 over I. Then I would have R equals to EMF multiplied by 1 over I minus R. Relate this to a straight line graph because you can see that this is a straight line graph. So this would be my Y. This would be my constant, it's EMF, I can call it A. or can call it the gradient m. M, then this is my x. This is my y-intercept. Negative r is my y-intercept. So do you guys see how you have to approach these questions? Find the equation first. Then once you found the equation, you know that, okay, the gradient is EMF in this case. It's not always like, I can't make you cram the graphs, guys, because you'll get a different graph. You need to know the process of getting these equations, right? So the gradient would be EMF. If I calculate the gradient of this graph, it would give me EMF. A question would say, write down the value of the internal resistance. You know that the internal resistance is the y-intercept, right? So that you take the value here, it's your internal resistance. They would say, calculate the EMF of the battery. They know that you have to calculate the gradient of this graph. Then once you found the gradient of this graph, it would be your EMF. I won't do that. Just wanted to show you how you approach the questions. Are we all on the same page? All right. Look at this one. This one is a problem whereby there is no internal resistance. Can you see how it differs from problem where there is internal resistance? Where there is internal resistance, we would expect the relationship between voltage and current to be like this. But then look at this one, it's an increase in one. So here there is no internal resistance, right? And if there's no internal resistance, we're just gonna use the Ohm's law. So R equals to V over I. So they plotted potential difference versus current. So let's make potential difference the subject of the formula. Potential difference would be equals to R multiplied by current. So this would be Y equals to MX. So the gradient would be the resistance and X would be the current. Look at this one here. This graph, this pink graph, has a steeper slope. It's steeper, you see, and this red one is more gentle. So because of the red one is more gentle, its resistance is less. So this one has a less resistance. They used less resistance. Here they used a higher resistor. When conducting this experiment, they used a higher resistor, and here they used a lesser resistance. So you see, they do ask these questions, guys. Look, what physical quantity does the gradient represent? You can see it represents the resistance. Calculate the slope. Because you know what the slope represents, so when you calculate the slope, you need to include the unit of that quantity, right? So we would calculate it and say that it's in ohms. Determine the resistance of R1. Right? Okay, I don't have the graph here, so Elena investigated the relationship between V and I for the combination of two resistors, R1 and R2. The graphs of potential difference versus current for the combination of two resistors in series and in parallel. Oh, okay, so one should be in parallel and the other one were in series. So which one was in series? Under which one were they in parallel and under which one were they in series?
In X, they are in series, and then in Y, they are in parallel.
Yes, that's correct, right? Because of if they're in parallel, we would expect a lesser resistance, right? So R1, R2, this is in X. Sorry, this is in Y. Then in X, they were like this. R1, R2 in series. R1, R2 in series. Right, so this one would result obviously in a higher R total. Right, so So how would you determine the value of R1? You'd have to use a simultaneous equation. Do you guys see that? Do you guys see that you have to use a simultaneous equation? Because look, you'd say that you take for the parallel combination. This was a good question. For the parallel combination, R total 1 over R total is equals to 1 over R1 plus 1 over R2, right? So, okay, if we calculate, so for X, sorry, not X, for Y, let's wipe this, okay, for Y, we calculate the slope. So let's use this point and that point. So our slope would be 0.50 divided by 0.50 for Y. Yeah. So that would be our R total here in Y. R total would be change in Y over change in X, which will be 0.5 minus 0 over 0.5 minus 0. So that's 1. So for the parallel combination, our resistance is 1. So 1 over 1 is equals to 1 over R1 plus 1 over R2, 1 over R2, right? So this would be equation 1. Then for the series combination, R total is equals to R1 plus R2, right? So R total for the series combination, it will be the gradient of this graph, right? So look at the gradient of this graph. I can use this point and the 0 is to 0, right? So the gradient would be 2 minus 0 over 0.5 minus 0. So 2 divided by half, it's 4, right? So R total is 4 here. So I would have 4 is equals to R1 plus R2. Then I created two equations with two variables, then I can solve them simultaneously. But remember, they want us to solve R1, so we can make here R2 the subject of the formula. So R2 is equals to 4 minus R1, then substitute this there. So I would have 1 is equals to 1 over R1 plus 1 over 4 minus R1. Then I can solve for R1 here. Yeah, it's going to be a long one. Multiply everything by the LCD. So our LCD here is R1 into 4 minus R1. This is maths, guys. So I would have R1 into 4 minus R1 is equals to, when I multiply this by that, the R1 will cancel the R1 and I would be left with 4 minus R1 multiplied by 1, which is still 4 minus R1, plus when I multiply this with that, the 4 minus R1 would cancel the 4 minus R1, then I would have R1 multiplied by 1. So you see that this would cancel that. Then I would multiply everything here. 4R1 minus R1 squared is equals to 4, right? Then I have negative R1 squared plus 4R1 minus 4 equals to 0. Then use your quadratic formula, find R1. It was an interesting question. Eh? I don't know if there was a shorter approach, but that's how I would do it. It makes sense to me. Look at another graph. Here's another graph. Like for these graphs, guys, you need to know what the y-intercept represents and what the current represents. And for specifically this one, that shows the relationship between V external and the potential, the V external and the total current. You must know this one by heart. Know this graph by heart. Know this one by heart. Know that the y-intercept is EMF. I explained this one to you, why the y-intercept is EMF. The gradient is negative internal resistance. Know this one by heart, guys, please. And you know how we got here, right? because EMF is equals to IR plus V external, making V external the subject of the formula. EMF is equals to negative RI plus EMF. So this would be Y, this would be M, this would be X, this would be C. So our M is negative R, our C, which is the Y-intercept, is EMF. Take the values from the graph, right? Write down the value of the EMF, take it from the graph. Determine the internal resistance of the battery, calculate the gradient, it's equals to the internal resistance. But then your internal resistance would be so you'd get the gradient as negative because this is a decrease in straight line graph, right? And remember, the gradient is not internal resistance, but it's negative internal resistance. So let's say you got your gradient as -4. You'd say negative R is equals to -4. Then therefore, dividing both sides by negative R is 4, right? So this is how you'd have to solve it. Guys, do you see that these graphs are easy? Remember, I told you that when we were doing electrostatics, that take that as a foundation and we're gonna build on it. Even when we get to electricity, how we approach the graphs, it's still the same. It's still the same, guys. So this is what we got in 2023. We just got a simple a simple circuit here. You see, it's like we're gonna draw the arrows, right, showing how current flows. You'd see that arrow coming out there as total current. The total current passes through the internal resistor, passes through the ammeter as well, passes through this point, and when it gets here, the total current splits. It splits into this one, right? I can call it this one IA and call this one IB, right? So IA would then further split as well into this one. I can call this one I1 and call this one I2, right? Then I1 and I2 would combine again here. I1, I2 would combine again here to give us IA again, IA. Then remember IB would flow down there, IB, when it gets here, it combines with IA to give us I total again, which goes back to the battery. And when you've done with this, you are done with the question. You are done with the question, right? You'll be able to answer everything here. So just attempt it on your own, guys. Explaining questions. Then you have 2022. This is what they got. Same approach, yeah. But you know, a session is not a session without multiple choice questions. So let's do some multiple choice. So we're done, guys, with electricity. Well, the only thing that we left with that I didn't touch on is cost of electricity, and it hasn't been coming. No, it does come, but it's not under electricity. It's under the generators and motors. Hey guys, your session starts at 8, ne? Your math session starts at 8, so I guess you'd have to leave sooner so that you can have a 10-minute break for maths. What's the answer to this question, guys? JM or A? How did you get to A, JM?
So it's because the V3 is equals to V4.
Yes.
So the V1 measures the V external, and V external is equals to V2 plus the V3.
Oh, yes. Yes, that's correct. Do you guys understand that this one? You guys understand Jaden's explanation? That's correct. So another way you can say that V total is equals to V of the series plus V of the parallel. Not V total, but V external, right? V external is equals to V in series plus V in parallel. So our external circuit is a combination circuit. As you can see, it has this series part and this parallel part. So our V in parallel is V3, or I can say V4. Anyone, they are the same, they are equal. So it's going to be V3 plus V2, V of the series, right, which is V1, our external voltage. Yeah, that's correct. Then how about this one? What's your answer to this one, guys? Yeah. Guys, what's your answer to this one? Jaden or B? Okay, why Jaden?
So I actually think it's V4C.
No tla pila ngwanaka wa ipota ngwanaka. It was B actually. So this is this is what actually happens in the exam. You give the right answer, then you think about it too much, then you give the wrong one. So the right answer is B, and I can explain why it's B. Remember, when no current is flowing, this voltage here, this voltmeter across the battery reads EMF. You see, this voltmeter is connected across the ends of the battery, on one terminal of the battery and on the other terminal of the battery, right? So it would read the EMF. It won't be zero. It would be the value of the EMF. But if you think about it, this one and that one, they would be zero. You know why they would read zero? Because look, they are not connected to the terminals of the battery, right? So if no current is flowing here, then it means that this thing just acts as an extension to the negative terminal, right? But then look at this one that has to extend to the positive terminal. It's being cut off. So this one here does not have potential, but this side still connected to the battery, but then this side is not connected to the battery. So it's going to be zero. So the voltmeter reading here is going to be zero. Same thing with V4. Look, this side is not connected. This side of the voltmeter here is connected to this positive terminal, but then this side needs to be connected to the negative terminal, but it's being cut off here by the switch, right? So it's going to read zero. But look at V3. This terminal, this side of the voltage is connected to the negative terminal. So this red wire just acts as an extension, right? Because there's nothing here, there's nothing else here. The resistor is also not working, so the wires are just acting as an extension to connect it to the negative terminal. Same thing with this side here. Everything else is just an extension. to connect it to the positive terminal. Can you see the V3 is still connected to the positive terminal? So it's connected to the negative terminal of the battery and also connected to the positive terminal of the battery. Therefore, it registers what? EMF when no current is flowing. So that's V3. V2 and V4 would reach 0. Okay, this one is cost of electricity. Kilowatt hour is a unit for electrical cost, but then it's have to be energy, right? This is electrical energy. We will talk more about it when we do cost of electricity. So let's conclude the session for now. But do you guys have any questions? So I gave you a foundation, guys. You know what to prepare when you do prepare for the final paper, guys. Just go there, practice more questions. I gave you the basics. I gave you the things you need to know. Please make sure that you prepare, practice as many questions as you can. You'll see that the questions are repeating, guys. Do multiple choice questions as well. Let me not take too much of your time, guys. Good luck with your math session. Yeah? We will meet again tomorrow. Good night.